Oh, it means you have introduced some more states in between CV and PD.
Yeah.
Okay. Okay, thank you.
Oh, thank you.
Okay, very good. So we'd like to wrap up at this point so that we can move on. Thank you very much, Ji-hyun Kim. So our next distinguished speaker for the invited talk is Professor, we're going to have Professor Jamie Paik from EPFL. And hello.
Morning or afternoon.
Yeah, good afternoon here. So good to see you here. So would you like to share your screen so that I can introduce you during a while? So Professor Jamie Paik is the director and founder of Reconfigurable Robotics Lab, RRL, of Swiss Federal Institute of Technology, EPFL, and a core member of Swiss National Centers of Competence in Research, Robotics Consortium. So RRL's research leverages expertise in multi-material fabrication and smart material actuation toward unique robotic platforms. And at Harvard University's microrobotics laboratory, she started developing unconventional robots that push the physical limits of material and mechanisms. Her latest research effort is in soft robotics and self-morphing robotic origami. So I'm sure she's going to share the topic on this amazing one. It drew my attention that the sentences drew my attention. While this novel technology has been published in multiple academic journals, such as Nature and Science and Robot, IEEE Transactions in Robotics, it also pushed the boundaries of the industrial applications of these robots, as seen in TED Conference 2019, and the latest Robogami is part of Mercedes 2020 concept car Avatar presented during CES 2020. So I'm sure it's going to be a really interesting talk. So the stage is yours, Professor Paik.
Hello, everyone. Thanks for having me on this 61st Summer Korean Vacuum Society Conference. What a history, and I'm very happy to be part of this conference, as well as the rest of the speakers who preceded me and is coming after me. So today I want to talk about the exciting research topic I've been pushing for past a couple of decades. It's called Reconfigure Robots, and that's the name, also the name of my lab. It could sound like an oxymoron, reconfigure robots. Well, robots are normally designed, classically designed to do one thing, and one thing really well, better than human counterparts, better than other machinery, having the intelligence to do something better. And this betterment is normally measured and quantified through their mechanical performance, force, speed, accuracy, precision. But my lab and my research interest actually relies something a little different. What if we make them do multiple things that are unknown from the moment of conception and do them well? Have the mission not be failed, even if the environment changes or the task changes at the last minute. And I think what's most important for doing that or achieving that is having the intelligence within the body and having the intelligence within the interactions between the machines to machines, robots to robots, robot to humans, and automated system within our society and environment. So my research really encompasses how do we bring design, control, and assembly that is more intelligent to make this interaction more intelligent, not necessarily all controlled. So one of the things I think is really exciting for many of us in domain of science is origamis. I take inspirations for origamis a lot because this is a platform that is seemingly very jolly and playful, but also it's the same platform that really transforms from one shape to another without actually having to change the platform. It's initially a same integral platform, which is in this case, piece of paper. And depending on how it's folded and how you're changing the sequence of the fold, it creates different forms and shapes. And not only that, it changes the dimension. It starts off as a quasi two-dimensional platform, but depending on what you're folding into, it becomes a 3D object that's changing forms. What if you had an automated platform that actually does origami itself? So when it's completely flat sheet of robot in the beginning, as you see in the animation, it won't be able to carry out its mission on the other side of this small opening. But if it were to crumble its body, changing the form, it can actually have additional functionality by going through this small opening and executing a final mission. It's a very crude and very simple example of how form gives additional functionality. But imagine if we do more than that. What if we create more forms that create more functions? And that's where the origami concept comes through, no pun intended. Okay, let's go to the next slide. There we go. So what are the actual engineering and scientific challenges? Well, if you want to have a flat form of automated system that really, it can be programmed to fold into different shapes and different sequences, what do you actually need? Well, you need to have all the core components of robot in a single platform. That means you need motors, sensors, processors, electric circuits, all on the same body. This is quite difficult because not only it's a small or very high, depending on which ratio you take, high or small form factor, but also you have to keep the integrity of all the core components throughout the transformation. So where do we get the idea how to manufacture this? Well, we take advantage of an established manufacturing process, MEMS. In the established MEMS process, you basically go through this process. Let me just start the video from the beginning. Well, you take the stock material, in this case, a PCB material. You laser cut out the actual shape, the final shape you want to have. And then you multi-layer press, multiple layers of sensors, actuators, circuits, whatnot. And then you place discrete components that are not necessarily origami made for the flexible folding. But really the magic or the uniqueness of origami robot happens right at the end. Once the assembly is completed, coming out of the oven and reflow oven and then including the final assembly, the major difference is a transformative. It's self-folding. You create a completely quasi 2D platform of assembled stock, basically a stock of non-autonomous materials that are intelligently designed to put together. But at the end of the conveyor belt, you're able to create a self-transformative robot. This basically means you're not getting a component out of the final assembly. You're getting a finally assembled robot at the end. And this is quite exciting concept, and very powerful for that matter. The reason is that because you're taking advantage of the quasi 2D manufacturing process, you can pick and place literally different processes. Different materials can be added in the middle. You can add additional punching. You can add additional pressing process depending on the final design. And what does that mean? Well, we're able to close the loop, a physical loop of closing and customizing your robot that responds to specific commands. You can actually have an on-demand supply of robots that is design iterated, and manufactured at the final output. Well, so far in my lab, we don't achieve every single one of these tasks, but we have examples of robots that are taking some of these tasks and realizing it. But in the future, what we are imagining is that because we can take advantage of this push button manufacturing that can be called in demand or on demand, we're able to add additional intelligence within the system. Having additional intelligence within the system with additional layers or different design changes will allow us to do a more interactive interactions with robots, with environments. So some of the tasks that we are currently able to achieve, some of them partially, some of them together, are computation, communication between robots, cooperation between the robots, manipulation with the environment, and mobility of their own. And if you want additional customization because you want to add additional sensors, because sensors, the extent of sensors improve every day from the academic part as well as the industry part. So if you want to customize it further for adding different sensors, for example, with Professor Sung-Gu Kim, we are looking at different sensors that's measuring the biosignals or gas leaks. So say we want to add those additional sensors on adding an application field. What do? We change our parameters that goes into system design. Not necessarily in geometry mechanism, but the fabrication sequence additional sensor layer. If the sensor is too big or too thin, then we would add additional layer that is inserted and updated in the geometry. And that will update the most important fabrication sequence. Basically, it's the same type of design parameters we are very familiar with when we're using 3D printer. But what is different here for this robotic origami process would be adding this fabrication sequence. And that would allow, and then we call this a universal design library. Once you have the design library updated from your application field, you're able to go through the same conveyor belt process. But compared to the previous robot, probably will have additional material, additional pick and place due to the additional sensors. But at the end, it will go through the assembly process, self-assembly process, and create a 3-dimensional robot. Why am I keep mentioning a 3-dimensional robot that's coming out from 2D dimensional manufacturing process? Well, as engineers, we understand bigger the dimensions, bigger the complexity of building of anything. Bigger the errors, bigger the higher resolution, achieving higher resolution more difficult. And having robots that are have at least multiples and hundreds of components, if not thousands, having this dimensional change to be minimized actually allows us to have a very accurate and very loyal robot to its design. And imagine if you want to have a swarm of robots, it can drive down the cost very effectively without jeopardizing its mechanical as well as electrical capacity. So here is a couple of examples of the robot that are based on this design theory as well as the design parameter changes. So like I said, we start from the quasi 2D manufacturing process. So you see that on the left-hand top as a GIF file. So it's designed as a complete triangle and then self-folds into a crawling robot. But what was I talking about earlier in the presentation was that we want to have a robotic interface that's intelligent enough to interact with the environment, but not necessarily by losing its additional weight, adding additional design change, by iterating by the cost of having just additional stuff. Here's an example of a single robot, a tribot we call, with 3 legs. It is able to change its locomotive pattern autonomously, depending on its terrain type. So what you're seeing here is that with this crawling type, locomotion type, it's able to crawl across a flat ground. It's doing the sort of an inchworm motion. Well, if you were to meet this something else, for example, no longer a flat surface, what can it do? Well, normally you would actually change its program, or for any other robots, you will change a different configuration completely. Well, here now it jumps and hops over. And if it has a free time or it's going over a staircase, it creates a bigger a slingshot type of motion. And same thing for the somersault jump. We're just over the Olympics. It's playing Little Olympics on its own as well. So the form or the actuation sequence can actually give additional functionality. Currently, these are very lightweight. As you can see from the rulers, it's about a palm-sized robot. What we can do with this is that you can have multiples. In our lab, we don't have the conveyor belt and we don't have the automated system that allows us to do the mass production. But with our students, what we're able to do is create about 10 of these to actually display how they're able to communicate with each other and execute tasks that are a little more difficult for such a small robot with a limited functionality in terms of sensing and communication. And this is very much analogous to how the nature behaves around the environment and with much agility. For example, ants do the exactly same thing. The individual ants are not that strong, but in groups, they can create bridges over the stream of water. You can create food sources that's way far off compared to their body length. So we can imagine having this type of origami design platform. We can create interfaces that are much more interactive with the environment, as well as interactive with the users, because you can update its design according to this changing environment. what you just saw before was a single platform origami robot that can do multiple tasks depending on how you're activating different joints. What if we can actually make this modular? Modularity robot means different things for different labs, but in our lab, it means having a single module should be functional, but you will gain more functionality by adding more modules around. And the fact that we can have heterogeneous modules, meaning you can have the active modules that you see on the left top with 3 motors on a triangle base, combined with passive modules, which are completely open triangles. By combining them in a different fashion, meaning different numbers and different combination of numbers of active and passive, you're able to create this design space that's much larger than the single robot. Well, the single robot is, it's cute. It can crawl across a flat screen, but you cannot do much more than that other than going place one to be. But if you combine these passive modules, which are supposed to be much cheaper than the active modules, they are bound kinematically from one to another, and it allows us to create a bigger task base as well. Bigger design space is equivalent to the bigger task base for us, and that really pushes us the limit on what else we could do and what else could we do, objects from left to right. So these are a couple of examples that is analogous and that draws a similarity to the more classical tasks. But what is a task that goes beyond our classical task? Well, think about video games. Have you ever saw like a video game and you thought video game or computer graphics and say, well, I know that's CG, that cannot be real. If it's CG, it cannot be real. Could we change that phrase and say, well, if it's CG, it could be real? What I'm trying to get at is that when you're trying to create an environment, a physically viable environment in CG and computer graphics, what you do is you add a physics engine into the graphics. And how do you do it? Well, you first dissect the elements in a smaller meshing format in a polygon, and then you apply structural mechanics, the behavior of material in these small mesh structures. And then once you're assembled, you have a more realistic structure, either by surface rendering or by actual physical behavior. Imagine if you can actually do this in a physical world, not just in the computer graphics world, but in the physical world. Well, what happens is that you have individual meshes that are in the smallest polygon, so it's triangle. Those triangles will change its resolution by the size of each module, but they're not necessarily equilateral triangles. So if you could have a robotic or a physical representation of these polygons that change its distance, meaning you will change the parameters of this triangle to create completely equilateral triangles like this, but that squishes or swarms into a different edge length, then you're really able to create a physical representation of a computer graphics. Of course, the disclaimer is the resolution has to be really high. The edges should go very minuscule to very large, but the concept-wise, it's something that is approachable. And one of the things that we were trying to do with our industrial application is that maybe we don't need to be so upset with a resolution, but if we already can achieve a multiple degrees of freedom surface from a single surface with not much of a payload based on the number of degrees of freedom, meaning payload comes from the motors, number of sensors, maybe we can achieve further of this interactivity. So this is an example of how we are using our origami robots for industrial application. This is a back of avatar car and the Mercedes-Benz. So this is the side, this is the back. Normally, this is where the airfoils would go in the back of the car. So you see this airfoils on the back of the car that's much bigger and many more than what you would normally have. Every single panel pops up and rotates around 3 degrees of freedom. It was not necessarily excuse me. It was not necessarily designed for actual changing the aerodynamics of the car, but it was designed to show the interactivity of the car driver with the people who's at the back. So it's a very much of a socially aware car concept, but having that's a very flat panel that creates high degree freedom allows us to actually go for how the modularity of the system can add additional layer, literally layer of complexity to a surface that's meant to be a completely flat. Here's the next one. So if you were to have this many degrees of freedom that I was making illustration as well as analogous example to the multiple foils of a car, how would you control them? Controlling individual degrees of freedom is always a challenge for many scientists and roboticists, let alone multiple degrees of platform that are distributed over a different surface. This is going to be, this brings up the complexity of control by exponentially. One of the ways I think is, which I really argue for, is intuitive way of controlling. So this is how we control our origami world with multiple degrees of freedom. We have a physical representation where Jennings holding under his fingertips, as well as a virtual representation, which you see in the screen. And because they're kinematically constrained to each other, the board itself, we're able to take the intention of the user, how they want it to be controlled, and then transfer and interpret it into the visual surface. And if it's not exactly what he wants to actually achieve, we're able to control the trajectory depending on the system. And not only that, since I was keep mentioning the interactivity is super important, what if you don't all have a physical representation of origami robot? Not to worry, it's much easier to have a virtual platform, but then you would actually have access to the physical platform that's on the other side of the world in a different time zone. And what's unique here is that not only the virtual user can actually control this robot interface, but you can have a second master who will be controlling this by touching as well. So you would actually feel what the other master one in the virtual world, master two in the real world, are feeling from each other. And that really is the handshake of using robotic interface to transfer the intention, physical intention of one user to another. And this becomes a quite important topic for us. I know I'm tight with time, so I'll just go a little quickly from now on. But if you think it's okay, I'll try to slow down after a while. But the application for this physical interaction with another person in the other end of the room, other end of the galaxy, or in the space, is really in space. Astronauts are highly trained professionals who are out in the space. But what they don't have access to is actually going out in the space location if they're not programmed or they're not trained to do so. There are astronauts on the ground, but not necessarily, not all of them can go into space. So we need to have a robot that's representing our intention for the exploration. And it's really expensive to bring robots when you don't know what environment they will be working in. And even if you have defined this environment, the tasks change all the time. So what are the ways of introducing robots that can multitask, that's more interactive with a different environment? Well, how about modular origamis that can interact with environment by changing its form factor? And here it's our idea of changing its form factor to do different types of exploration tasks on the ground, under the ground, and above the ground by changing its body shape. And having too many modules won't matter as much because microgravity will help out us a little bit. And not only in the outside of the space station, you can actually think about how these interactive nature of origami robot concept can help astronauts to communicate with between each other, but also with people or the scientific staff on the ground. So what you see here is examples of, this is a zoom in images of how the astronaut can potentially use these modular systems. So modular systems that are interactive when you need actual helping hand to conduct experiments, communicate by having an interface that gives you physical interactivity with different profiles, different topology measures, as well as different stiffness rendition of objects. You can actually create interface that is realistic in terms of its physical behavior to different experiments, as well as what the instructions are coming from the ground. And then having these extra helping hand as if they're interns in your space station. We don't have to go too far in terms of this interactive interfaces, interactive machine and human interfaces, because we are actually experiencing right now as part of entertainment and robotic surgery, which means we are using haptic interfaces. Current haptic interfaces and virtual reality environment is heavily vision driven. You have a very great graphics, very realistic. It's taking advantage of physics engine, but you can say it's still virtual because it's not tangible. It's you keep your hands up in the air because you want to actually feel what you're seeing, because what you see as an image and sound is very realistic. So the studies of trying to give this additional the handling and the feedback in the hands is called the haptic interface or haptic feedback. There are different ways of achieving this realistic feeling. One is a cutaneous feedback, meaning it's a skin level feedback when you get the skin level force feedback, and the kinesthetic feedback. That means that you're actually moving to interact with the environment. And as you're moving, and then as you have the force feedback, then you actually feel that you're interacting with the environment physically. And then at that moment, your interface or your experience is no longer virtual, but it's actual physical and more real. What do you need to achieve this type of cutaneous and kinesthetic feedback? You need highly interactive interface that interacts with you, and then recreating this virtual environment to a physical environment. And that's where we apply our origami robots design principles. And beyond that origami robots, we have this soft silicone-based wearables, soft silicone-based interfaces that also gives you a cutaneous and kinesthetic feedback. So what you see in the red circles are the area zones that we're giving the physical force feedback. And they're laid out by the magnitude of forces that are able to create. So more sensitive ones for the fingertips, we give about 1 Newton of force that's modulated with different frequencies. But also for the lower back or upper back, we require, which is a little more dense in a sense, where you require higher forces to give a really realistic feeling back into your body. This is an example of how the cutaneous actuators are put on our fingertip. It's so thin that you don't feel it's on, and you only feel it when it's activated. It's currently not necessarily in glove format because glove has its own difficulties, but the contribution of this work is in the fact that it's thin and it's creating a large force as compared to any other existing actuators, as well as high frequency. When you combine modulation of force with a high frequency, then you really create an organic feeling or organic feeling back to your body. And that gives you a feeling of actual interaction. And let me just go through. So this is also embedded with sensors. Here we have a liquid metal sensor that's developed from a course group. And we're looking forward to having different sensors from students through collaboration with the Professor Kim as well. Different platforms that allows us to use this actuator distributed around the arm, forearm, and using the same platform to use it as a wearable tactile interface for messaging, as well as receiving like a phone call. So messaging as well as a phone call directly on your skin. And we are able to find as a 4x4 grid, you're able to create and remember multiple words that is able to create the short sentences. And let me see how far I can go. And then you're able to use the same interface to actually prove that you don't necessarily have to rely on vision to create and transfer information, meaning that it's just purely from the vibrations under your fingertip, we sent out messages of actual form of what kind of object we want them to test out. So here's an example of we sent out the images, or not images, virtual tactile images that is only transferred by hand. And by doing so, we are able to ask the subject to create the object they felt. So if you send an image or the virtual image of the sphere, square, and prism shape, they're able to recreate that just from feeling replicate the form they were actually touching. So it's basically a blind feeling the different objects and telling you what they're feeling. And that is actually what we do for normal people without the vision impairment. And we have different versions of it using origami platform that you can have different form factors as well as stiffness renditions underneath your palm. So I can go over these ones a little later if you have more questions, but I will just go straight back into our, and that being said, I hope I have sort of intrigued your ideas, intrigued your senses, no pun intended, in terms of how soft reconfigurable robots can really be used for making human to robot interface much more interactive and much more real. And that I think is really important for, especially for medical fields, especially for people who are during this period of pandemic. I just want to thank my students who are the key anchors of producing this amazing ideas and pushing that through, and my funding sources. So that is for me. Thanks for your attention, and I'm open for questions.
Okay, thank you so much for the fascinating work. So sharing the fascinating work. So if there's any question or comment, we would like to take one.
I have a question.
Okay, go ahead.
Can I ask you something?
Jonghwan, would you want
Yes.
to start first?
Okay. Thank you for your presentation. I show your first device has layer by layer structure and junction connection. You are saying that press manufacturing process that is combine each layer. So I want to ask that layer by layer inside some adhesion layer and or that junction side and that layer structure, how to attaching that each?
That's a great question. That's the most difficult part, actually. It seems really simple. It's not a sandwich. Sandwich, if you put different layers, you don't care if it falls apart or not. You put a toothpick on and then you store the holes together. It doesn't matter. You just eat it away. In terms of robots, it's not as simple. So we use this toothpick method where you do the anchoring points for vias. But obviously, if you made a multi-layer PCBs, making via for just PCB is very complex. So you have a different manufacturing process for that. But if you're adding additional circuitry, additional sensors, it gets even more complex. So what happens is that we make sure that design-wise, multi-layer design-wise, they're sound. And as you said, the via point, like electrical via points, mechanical via points, fixation points, they are the weakest part of the sandwich. So if you were to experience any type of failure, that will be the failing part. The adhesion layer is somewhat easier because the adhesion, that sort of refers to having a surface area where you actually have adhesion happening. But if you're talking about the via points, mechanical via points, and then electrical via points, they are the most challenging ones. Currently, we are also looking into using, or actually we've been working on using actuators that are not electrical motors or ultrasonic motors. In that case, they have a pneumatic supply, meaning we actually have a tubing that goes into the system as well. So making an untethered system or even multiple layer system with this multiples of different components with different characteristics, it's quite challenging. And a lot of papers from our lab actually addresses how to make this layering possible. So thanks for a great question. I really did not go into that, but yes, that's the biggest challenge. One of the biggest challenges there, for sure.
Thank you.
Okay, great. We probably we can sacrifice our concluding remarks so that we can take one more question from any other students.
Can I ask you something?
Go
Sure.
ahead.
I want to check some point. First, you mentioned about that more form is make more functions. It's like for the origami structures. So this structure's advantage is more form makes them more function, right? So you mentioned that. So I have some curiosity. After you mentioned that the first assembly, it is automatically assembly themselves, like that robot. First assembly, after that, we decide to convert to the purpose, like first time the communication to the other manipulating or something. So after that, how can transforming that part?
How, sorry, the last part I was not, I could not hear you. So how is the last what?
When we are trying to change our purpose to use a robot, right?
Right.
Yeah. After first assembly, how can we
How do you decide on the
transforming-
form is what is optimized for the task? Is that what you're asking?
Yeah. Because I
Okay.
have some curiosity of that. It is uncostable for the attaching all sensors or communication devices or the one device.
Right. So I think it becomes a more philosophical question. So when I said the forms follow the function and function follows the form, it was really set out in the more general terms of idea. And it's fact when you're talking about if you have if you have a fork with 2 tines compared to chopsticks that is held by a full hand. When you have a fork, you only need 1 degree of freedom, go in the Z direction, pick up your food, whereas chopsticks require more degrees of freedom and even in the manipulator to use it. And then we say, well, chopsticks with more degrees of freedom allows you to have more versatility in terms of picking tasks. But it doesn't necessarily mean it can attack all different problems. You cannot pick up your backpack with the chopsticks. You may, but you will sprain your wrist. So yes, when I'm arguing having larger degrees of freedom allows you to have a larger workspace, is purely based on relative and comparatively. But it leads to a really important question as well. How do you decide which form is best comparing how many degrees of freedom you have? You have so many different design options, so many different transformative options from form A to form B and form C. How do you decide if you want to have form B? How do you decide what is form C and B are? How do you decide it? Well, it depends on the actual task at hand. And we are not exploring in that the transformation optimization to that extent. Currently, our robots are not as complex as we want it to be. So we already see the limits in terms of the torque, the bandwidth, the range of motion wise. We already see certain limitations. Of course, they can be enlarged with additional modules, but currently we're at the stage of showing what is the limitation of a current setup the robots are and what can be extensive nature or extensive task space if we were to change that. So one of the examples of right now what we're working on is, remember I showed you the meshing pattern of the triangles? I said if you have an equilateral triangle, there is a limitation of how far it can go. So we're changing the length of the equilateral triangle to change its form. So you start with the same triangle or the same length triangle. And then depending on the task, we actually extend one length further. So we actually have like this squishier triangle or like the skinny triangle. And what we are showing there, and that is what additional 3 degrees of freedom onto that single platform compared to having a rigid triangle form, even though that moves on the sideways. So one of the studies we were showing is that by having this heterogeneous module, because the module itself is module, but the length are changing. So heterogeneous module, we're able to create bigger workspace. So that's how we're approaching this topic of how do you justify having larger degrees of freedom actually gives you more functionality. So that's how we're approaching it. But if you have other ideas and if you have other ideas of how to objectively parameterize this versatility, I'll be happy to talk to you again. Thank you.
Okay, thank you very much.
I have a question.
Oh, okay. So, okay,
Yeah.
one more.
Yeah.
Please be quick.
Yeah. Thank you, Professor Jamie Paik, for giving such a wonderful and energetic presentation. So you have presented wide varieties of like haptic and robotic, origami, and different kinds of like sensors or devices, whatever it is. So I have a question on origami. So when it comes to the mechanical performance, so whether they are slow or fast, so how we can maybe overcome those things. So maybe, yeah, can you comment on those things?
So I think you're referring to the bandwidth of the system. Well, I guess it really depends, right? The bandwidth of the origami system?
Yeah, like maybe the performance in
Actuation
terms of
bandwidth?
the speed. Performance in terms of the speed.
Right. So the actuation bandwidth really depends on the actuator source. So currently we have multiples of solutions. So we have ultrasonic, we have pneumatic, we have a rotary, we have linear. So they all come with their own bandwidth that's innate to their actuator performance. We don't necessarily use to the full extent of their maximum performance, because for us, what we are trying to show as well as understand is how does reconfiguration extend its task base. And obviously these tasks are not that, currently it's not critical to the speed. Where the speed of this transformation would be very critical would be in terms of environments or medical robots. So medical robots, they use tendon-driven systems, so they are faster. But then again, we're not really doing benchmarking specific instrument to increase the mechanical performance in terms of their bandwidth, at least for now.
Thank you, Professor.
Okay, thank you very much. So I'm sorry for those who want to stay forever with Professor Paik, but we have to let her go now. Thank you so much, Professor Paik.
Thank you very much.
Yeah, so we would like to move on to the last but not least speaker. So our last speaker is Mingi Kang from Sangyungan University, and I'm sure he's ready.
Yes, I'm ready.
Okay, so would you want to share your screen and start your presentation? Thank you very much.
Thank you. Wait a minute, please. Yeah, thank you for your kind seeing me. And I am Minki Kang in School of Advanced Material Science and Engineering at Sangyungan University. I am in Professor Kang's group. So today I'm talking about wearable virus blocking textile for SARS-CoV-2 using human body triboelectric energy harvesting. So here are my contents, and starting from introduction, in 2019, SARS-CoV-2 started to spread, and a growing number of people globally are infected. Vaccines are long-term solution and fundamental solution, but it takes too long time and target just only one virus. To compensate this and to mitigate the spread of SARS-CoV-2, wearing facial mask will be an effective strategy. In prior studies, the respiratory virus such as SARS-CoV-2 is transmitted through the respiratory particles such as aerosol droplets. So electrostatic filter and mechanical filter are used to block the virus. But the blocking efficiency is lowered by fast degrading electrostatic charges on electrostatic filter, and SARS-CoV-2 is known that to survive on the surface of filter, so it can cause possible secondary infection by contact. Finally, they have low blocking efficiency if the particle has high speed or small particle size. Besides, enveloped virus such as SARS-CoV-2 is known that to have negative electrical charges. So we thought that repulsing or attracting virus by electric field would be available, but there was no experimental investigation on charges of SARS-CoV-2, and there was no principles to control with Coulomb force. Before I I explain my concept, I want to introduce the overall background of triboelectric energy harvesting. Energy harvesting is a technology which converts abundant energy to useful electrical energy. For example, triboelectric energy harvesting convert mechanical energy such as breathing, organ movement, body movement to electrical energy. So to power biomedical systems or electronics. Triboelectric nanogenerator generate electricity based on the coupling of triboelectrification and electrostatic induction. In case of triboelectrification, it is a phenomena which generate surface charges after contact between two different materials. So my concept has two backgrounds. First one is human body can generate electricity and can be a triboelectric nanogenerator. Because human body can generate triboelectric charges and has capacitive properties. It can be a good medium of electrostatic induction. So as you can see, when we attach electrode on some point of our epidermal position, output current is generated, which is enough to illuminate the LEDs. Secondly, SARS-CoV-2 is found. We found that SARS-CoV-2 has also negative charges through evaluation using electrometer. So here's my concept. We designed virus blocking textile VBT, which is textile capacitor. By using human body triboelectric energy harvesting, we charges VBT, and negative potential of VBT can repulse SARS-CoV-2 aerosol from infected person. So as you can see below, human body can generate up to 300 microampere current. Also, through ex vivo experiment, which may make respiratory contact using SARS-CoV-2, we found that virus in VBT drastically decreased 92.3%. So we characterize the upper performance of human body. So when we contact with PTFE or nylon with naked hand or latex glove, it can generate from 20 to 80 microampere current. So it is enough to charge VBT of 0.25 microfarad capacitor to 180 volt in just 3 minutes. So it can be a promising powering source of VBT. Also, human body can be expressed as circuit model, and calculated output was very similar with our experimental data. Furthermore, it is noteworthy that foot tapping or working or even fluttering of clothing can generate electricity. It means all kinds of human behavior which make contact and release separation can generate the electricity. So accordingly, we designed and fabricated VBT, which consists of 2 PWPSS coated silk textile and non-woven filter between them. So PWPSS silk textile is fabricated by just dipping and annealing simple dyeing process. So finally, we carried out ex vivo experiment which mimics respiratory contact. So to evaluate the virus blocking of VBT, we measured virus copies in front, VBT, and back. As a result, we found that 99.5% of SARS-CoV-2 is repulsed and 99.95% is blocked by repulsing the particles. So our VBT has several advantages and provide breakthrough. First of all, it can provide continuous blocking through self-powering using human body triple energy harvesting. And there is no surface virus eliminating the possibility of secondary infection. Third, they has high blocking efficiency of 99.95%. Furthermore, weak gas, it can be a general solution for mitigating spread of variants or future emergent viruses, because most of enveloped virus has negative charges, so we can repulse using VBT and block them. So in summary, we investigated highly effective virus blocking using clone force and energy harvesting technology. Through the combination of human body and cloning force, we achieve continuous high blocking efficiency, no surface charges, virus blocking technology. Also, it can be applicable to general enveloped virus. Thank you for my advice, Professor Sang Kim, and my colleagues in our lab. Thank you for your attention.
Okay, thank you very much. And I'm very sorry for everybody that we are quite in the delay. So if there is one quick question, we would like to take one.
Hello.
Oh, okay.
Can I ask? Yeah. Thank you for your interesting talk. And I wonder how to measure the signal from your device.
You mean triple electric output performance?
Yes.
Yeah, it is same with the video which I showed you. Just attaching hydrogel electrode on the skin and through wiring, and we used oscilloscope. So oscilloscope and current amplifier, and we just measured the current. And in that case, with another hand or foot, just when we just tapping on PTFE or nylon film, we can measure the output current.
Okay, thank you.
Thank you.
Okay, thank you very much, everybody. So we'd like to wrap up at this point. And before we go, we'd like to listen to Professor Sung Kim's concluding remarks so that we can say goodbye. Thank you very much.
Okay, so many thanks to the big contribution today. Especially was the invited speaker was joining the conference in late time in USA and Europe, and this conference for the young scientists is the design due to COVID-19 is that we cannot study and explore for global research. We wanted to give you the big opportunity was the students joining or the study in a global research from the famous professors. I hope that it will be the great chance you are learning about the big research part, and the symposium is designing every year. This year we finish in this moment, but this next year we also invite several famous professors, and then we will design for the youth symposium next year. I hopefully meet the next year. Okay, thank you for today. We will close of this frontier material for the young scientists this year. Thank you.